Hello. All right, we should be live. We got Nancy here. We got Chad here. Oh, I didn't put the card in. Oh, this always messes things up. Apologies in advance. I'm going to have to turn my camera off. Oops. I knew it. Okay, hold on. That's weird. Unable to use the memory card? Huh, I gotta turn my camera off for a second. Okay. Same background as last week. Do you want me to pick a different background? What do you want, Chad? I mean, you replaced the background anyway, so it's really just for the people who are watching the live stream. But go ahead, Chad. What do you want as a background? Let me see. What's new from NASA? I don't think so. The right switch? Let me try. Yeah, that recorded. Okay. We can do the NGC 6891. We do a postcard from Mars. That's a nice picture. All right, we'll do that. It's okay, I got it. I got you, Chad. We'll do Curiosity's postcard from Mars. There. Except it sort of shows the green screen. Grease. All right. There we go. Okay. Is there camera recording? Camera's not recording. Dealer's choice. All right. Okay. I'm going to start the recording. And start that recording. You should totally do a vote at the start of every show. Yeah, sure. Why not? That's a good idea. Okay. All right. So, as always, we're going to do a bunch of prepared questions first. And then we're going to shift in and do the your questions live. So, hit me with your questions. Let's do it. All right. Let's see. Everything is recording. Okay. So now I click on the live. All right. The recording reminder. Yes, I am recording. Okay. That's a problem. Okay. All right. Let's do the intro. Hello, everyone, and welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I'll answer them here. Now, I am recording this show live on my YouTube channel. I do this every Monday at 5 p.m. Pacific time. So if you want to come and hang out and get your questions answered, maybe some follow-up questions, come and join the live show, 5 p.m. every Monday. All right, let's get into the questions. Ed, when will NASA standardize a rover design? AKA, when will they build the workhorse Jeep that they can deploy over and over? It seems creating a new model every time you want to deploy a rover is too wasteful of resources and increases time between rover launches. It seems pretty simple, right? Settle on a unique design and then just use that design over and over again. But the problem is that the design for your rover has to depend on the terrain that it's going to be roving on. So if your rover is going to be roving on, say, the moon, then there's certain conditions, levels of gravity, amount of friction of the wheels, the size of the wheelbase, the temperature issues that it needs to be able to deal with. But if you're on Mars, then the temperatures aren't quite as extreme as they are on the moon. The gravity is a little stronger. You've got issues with radiation. So those are some of the big issues that you're dealing with. And of course, all bets are off. If you're going to try to go to an asteroid where the gravity could be so low that your rover could fall off the asteroid if it drives too quickly. So then when you look at the science payloads, the whole point of the exploration of a place like Mars, step by step by step, is to send a different suite of scientific instruments every time you come back. And they use different amounts of power and have different electronic requirements, different position requirements, different instrumentation, different kinds of actuators and robot arms and all kinds of things. And so when you put all of that together, you end up with a spacecraft, a rover, that is quite different in terms of its requirements from the previous generation. And they happen fairly irregularly. Curiosity got to Mars in 2012, Perseverance in 2020. So that's an 8-year difference, an 8-year set of improvements in technology. And you can really see all of the new incredible technology that went with Perseverance that weren't available with Curiosity. So you got this technology change as well. And then you've got differing launch platforms. You've got what was happening with the United Launch Alliance and, with Boeing and Lockheed Martin and such, and Arianespace 10 years ago. And now you've got this faster cadence with the Falcon, with what SpaceX is doing with the Falcon 9 and the Falcon Heavy and so on. And it would be great to have just a standard chassis that you send all the time. And in theory, you could then mass produce them. But you're never going to mass produce at the kinds of levels that would make sense. You're not going to build 1,000 rovers with all the same kinds of capabilities. You're going to build one, and then 10 years later, you can build another, and so on. But that's today. You can imagine that there will be some future time where the launch costs have brought the cost of sending a spacecraft to another world down very cheap, which means that you can build which means that you can build less complicated spacecraft, cheaper spacecraft, and not be so worried that because your launch cost is $500 million, you have to make sure that you build exactly the right rover. If your launch cost is $1 million, say with Starship, then you can send something kind of dumber and cheaper and stupider, and a lot of them. So I think we are going to shift over, but it's like a scale thing. And we'll get to some point where the launch costs have come down, the amount of space-based technology is so commoditized and so common that we will get to a point where we will see spacecraft mass-produced and sent out. There's going to be an asteroid-class explorer, and they'll send 100 of them out. And they all will have their own asteroid, and they're going to have roughly the same requirements. And there will be Mars rovers, and they'll send hundreds of them. Or Mars helicopters. They'll send hundreds of them. So just, we're at the beginning stages, but it will get there. You just got Flower of a question. When will James Webb launch? Oh, the 22nd now. Granville White. Question: if there is more space beyond what we can see because the light has not reached us, does that mean the universe is older than 13.8 billion years of age? From what astronomers can tell, the universe is 13.8 billion years old. And that is because there are multiple lines of evidence, but the main one is that you can look at the cosmic microwave background radiation, which is essentially the first light that was let out into the universe, and you can measure the distance to that when that light, or you can measure how long ago that light was released, and that tells you how old the universe is. And so that means that the universe is that age, 13.8 billion years old. But you got to sort of hold two versions of the universe in your mind. And it's not a thing that we do very regularly here on Earth. Like when you think about planet Earth and you think about all the places you could go on the Earth, you're imagining them as they are today. And that it's sort of like real time across the entire planet. People are watching television shows, they are eating breakfast in one part of the world, they're eating dinner in a different part of the world, and so on and so forth. But imagine if you thought about the world, about how long it would take you to walk. And of course, in the ancient times, that's the way it was. News traveled at the speed that people would walk. And so if some event, say there was like the death of an emperor, it would take time for people farther and farther away to learn of the death of this emperor. If you lived really close, you might learn in a couple of weeks. But if you were really far away, then it might take months for you to find out that this event had happened. And that's the same thing that's happening with the universe. The farther we look, the further back in time that we're looking, and the farthest that we can look is the earliest moment in time, which is shortly after the Big Bang. But if you could look at the entire universe in real time and not in this time-based, backwards-looking thing, then you would see a universe that potentially goes on forever in all directions. And there are galaxies this way and galaxies that way and galaxy clusters. It just goes on and on and on and on and on. And every part of the universe is existing 13.8 billion years after the Big Bang happened. But it's because light takes time to reach us that everything we see is older the farther that we look at it. Dave Redballs. Hey, can you talk about the best and worst entry-level telescopes? Reasonable price, I'm out of work, thanks to COVID, for backyard astronomy. Thank you, good sir. Man, it feels harsh to talk about the worst entry-level telescopes, but I will do that. Let's start with the worst. So the worst telescope is the one that you're not going to use. The worst telescope is the one that you're going to buy because you're really excited to look at space. You're going to buy it. You're going to set it up. You're going to try to use it. It's going to suck for whatever reason. Maybe the tracking is too difficult to make it work. Maybe the optics aren't very good. And you're going to end up being frustrated. It's going to collect dust and you're not going to use it. Or maybe you're going to be able to make it work with the moon, but any other object is just not worth it. You're going to get tired of the moon and you're going to, again, throw this thing in the closet, you're going to get rid of it, and you're going to be disappointed. So that's the worst telescope. And the way you avoid the worst telescope is you get what I think is the best telescope. And there's two paths to go on. And the one path is that you go down the visual astronomy route, where you just want to look at things in the sky with your own eyeballs and go, wow, I'm looking at Saturn's rings right now, or I'm looking at the moons of Jupiter. The other way is to go the astrophotography route. And I'm not going to talk about the astrophotography route because it is a multi-headed hydra all on its own. But we did a great interview with Ian Lauer, who is an astrophotographer, and we talked for about 25 minutes in the weekly Space Hangout about what's the best way to get into astrophotography. So I'll link that here and you can check that out. So I'm just going to focus on visual astronomy. And, many people in the audience are going to know what my answer is already, and that is the Dobsonian telescope, the light bucket. And what a Dobsonian is, at its simplest, is the biggest possible telescope for the cheapest amount of money on the simplest mount to use. And that mount is actually the part that's really important, because with a Dobsonian telescope, if you see an object in the sky that you want to take a look at, there's like a really bright star up there, you just take take your telescope, you look through the finder scope, you line up the object in the finder scope, you look through the eyepiece, and you're looking at the thing. It's got very powerful optics that lets you see, like Saturn, you can see the rings of Saturn. You can see the moons of Saturn. You can see the gaps in the rings of Saturn. Jupiter, you can see the storms, the Great Red Spot. You can see the Galilean moons. You can see Uranus, Neptune. You can see how Venus goes through phases. You can see the moon in just incredible detail. And then if you have any kind of dark skies, you can see lots of other objects. You can see globular clusters. You can see you can see galaxies, you can see emission nebula, you can see planetary nebula, you can see open star clusters. So there's really a bottomless number of things that you can see. They're cheap, relatively cheap. You can build them yourself if you don't have a lot of money. They're simple to use. They are just dependable workhorses, and I highly recommend. Like, if you can't afford a Dobsonian telescope, and for a smaller, like a 6-inch Dobsonian, you're looking at about $300. And if you can't afford a smaller Dobsonian telescope, I would wait until you can, or try to build one yourself and go with, say, a pair of binoculars until you can afford that level of a telescope. And that's the one that I really recommend. Okay. Okay, so those were all the pre-recorded questions. So let's get into the rest of the questions. So Chad, the used number of times is working great. This is awesome. All right. Peter Holbelsberger. With obvious signs of liquid water on Europa and Enceladus, why isn't there more of a push to explore? There's kind of a time lag from when astronomers make these incredible discoveries to when the engineers are able to build the spacecraft capable of actually exploring them. And so we've only really known about the geysers on Enceladus since the arrival of Cassini at Enceladus, well, at Saturn, but also Enceladus and the rest of the Saturn system. And Cassini arrived, was it 2004? I should write that down. Check, make sure I get that right. Yes, 2004. Okay. Cassini arrived at Saturn in 2004, and then within a couple of years, it was imaging Enceladus and revealing these incredible geysers that are blasting water ice into space from the southern pole. And so from that discovery, then, you've got to decide what kind of action you're going to take. We had a hint that a similar situation was at Europa, but it was actually more that the discovery was made at Enceladus first and then really mapped back to what could probably be at Europa. And once this discovery was made, the wheels started to turn to build some missions. And so, in fact, there are 2 missions going to Europa in the next couple of decades to search out this exact thing. NASA has the Europa Clipper mission, which is going to be focusing its energy just on Europa and trying to image the surface of Europa in incredible detail, trying to find the source of these geysers if they exist on Europa. And then the European Space Agency has its JUICE mission, which is going to be visiting all of the icy moons. It's going to visit Ganymede, Callisto, Europa, but mostly Ganymede, and try to see if there's a similar environment and situation there. And so it's just a time delay. The discovery, like up until the last couple of decades, the belief was that the only great place to search for life in the solar system was Mars. And suddenly Cassini showed us that, in fact, there are these icy moons that have water oceans underneath, and this water can somehow reach the surface and be ejected out into space, which gives you a chance to actually observe it. And so here we are. We're dealing with the discovery and the lag and getting to that point where we're actually going to be looking at it. Of course, as I say this in 2021, there are no plans to send a mission to Enceladus yet. And I think that's a shame. I do think that there should have been a mission, a version of the Europa Clipper sent to Enceladus. But we have the Titan Dragonfly. So we have a helicopter, a nuclear-powered helicopter going to Titan, which we think is one of the most interesting places across the solar system. You've got these bizarre hydrocarbon lakes. You've got clouds of material that look like some kind of early version of what the Earth looked like. And you've also got a liquid ocean underneath this thick layer of ice around the surface of Titan. So there's lots and lots of great reasons to go. So there's only so many priorities, only so much money for spacecraft, and NASA and the other space agencies have to pick their targets very carefully. Ted Krause. Dark matter. We know it's there, but we can't see it or prove it's there. Could it be a new element that just hasn't been discovered yet? I get a version of this question, which is that, like, could there be elements which are heavier, which have more protons than the elements that have been discovered right now? Like, if you look at the periodic table of elements, you go all the way up. I forget what the latest number, it's in the 120s or whatever. And a lot of those elements are really short-lived. You have to create them in a particle accelerator. You have them together for a moment, and then they fall apart and decay into other particles. And that's how, in fact, physicists are able to detect they even existed, is as they decay into other objects. And you would expect that in supernovae, which are the most powerful particle accelerators in the universe, vastly more powerful than anything humanity can build, are creating much heavier elements at their cores in this moment when they're creating all of the heavy elements, all of the gold and platinum and plutonium and things like that, as well as even heavier elements, stuff that we can't even imagine, that would then fall apart instantaneously. And in fact, it's sort of, I'm kind of tangenting here, I know that, but that is the evidence that there probably aren't stable elements farther up the periodic table of elements, because supernova would create them and we don't see them in the universe. Vastly more larger than anything we could ever create. So is it possible that there are elements farther up the periodic table of elements that could explain dark matter? And I mean, anything is possible. I mean, we don't want to close our mind to every possibility, but my assumption would be no, because matter, baryonic matter, which is what any kind of element would have to be, would fall under the same sorts of laws of physics that regular matter does. And the thing with dark matter is that it doesn't interact in any way, shape, or form with regular matter except for gravity. We don't see any radiation coming from it. We don't see any light. We don't see any magnetism. We don't see any we don't see it impacting each other. We don't see it bouncing into regular matter. It just doesn't interact in any way. And so if element 500 is the same as gold, except it has 500 protons as opposed to gold, then you would still expect it to give off some kind of radiation. You would expect it to interact with matter or regular matter in some way, interact with itself. And these are the things that dark matter just doesn't do. And so whatever dark matter is, and of course we have no idea, astronomers have no idea, it has to be something that isn't matter. It's something else. And what that something is we still don't know. Bomdia. What diameter do you suggest for a Dobsonian host? So, like, as big as you can afford is the best thing. The bigger the Dobsonian, the better. But like even a 6-inch Dobsonian, and they're relatively inexpensive, especially, I mean, if you search on the internet, you can find instructions on how to build your own. Really, you can buy the ground telescope. I should do this sometime just to show people. Maybe that's what I'll do. You could buy the blank, when I have more space, when our workshop is done. You could buy the blank mirror and the secondary mirror for like $50. You can put it in a stovepipe to make the telescope, as long as you just get the settings all careful. So they're relatively inexpensive, but like a 6-inch telescope, you're looking at about, like, on sale, maybe $250. An 8-inch telescope is going to run you more like. Scientists are using a kind of probe like this in Greenland. They've been actually able to test out. They take a kind of looks like a missile, like a dart, and the nose of it is heated up, and then they put it into the ground. In this case, they are using electricity to be able to run. It's connected by a wire, and they're able to have it go down through the ice at a pretty fast speed. Now, it would be even better if you had the heat given off by a nuclear reactor on board, say like a nuclear RTG, the same kind of thing you've got on Curiosity, Perseverance. This thing gives off a ton of heat and electricity. And so you would have this probe shaped kind of like a warhead or like a missile. It would sit on top of the surface of Europa. It would be heating itself up. It would tilt itself forward because it would be like heavier in the front, and then it would just start to sink its way down through the ice on Europa, spooling a line behind it, like a thin wire for communication with the surface. And then the water behind it would freeze back over and freeze this wire into place as the probe continued its way down. And depending on the size of the probe that you use, if you have a very long, thin probe, you can reach the water in like down 10 kilometers within like a year, even less. But if you've got a larger probe, if you've got a bigger science payload, then you're going to take a little bit longer, maybe 2 years, 3 years, depending on really just what is the cross section of the spacecraft or of the probe as you're sending it down through the ice on Europa. That's the best idea that's been thought of so far. And what I find kind of amazing is just how many places this technology has already been tested out here on Earth, and it all seems really feasible. Like, there's no reason why we shouldn't be in the process of developing a probe for this. So maybe that'll come after the Europa Clipper, is we'll get these really nice maps, these nice scans of the surface of Europa, and then the next will come the mission to try to get down into the ice, because that's where the life is going to be, is down under that ice. Wow. John Pritzlaff. Fraser, what would you imagine a war between two Type 4 civilizations might look like? What's a Type 4 civilization? I mean, a Type 3 is controls the entire energy of their galaxy. And so you would imagine like a Type 4 civilization would control all the energy within the observable universe. And so Type 4 civilizations wouldn't even overlap. So I don't know if they couldn't have a war. Bobby Reynolds. Do you know that supervoids... Oh, let's see. Bobby Reynolds. Do you think that supervoids like the Booty's void can grow from the expansion of the universe? Yeah, that's how voids grow. So if you look at the large-scale structure of the universe, the scale of the universe at the most zoomed-out view, you see these enormous structures, and they call them walls and... what do they call them as well? Walls. Oh, I forget what they're called. All right. Okay. So if you zoom out from the universe and you see the largest scale structure of the universe, you see these incredibly large walls of galaxies, galaxy clusters, each one containing hundreds, thousands, tens of thousands, millions of galaxies. These structures can be billions of light years long. And what's happening is that the expansion of the universe is trying to pull all these galaxies away from each other, but their mutual gravity is pulling them back together. And so what you get as the universe is getting less dense over time, as these galaxies are pulling themselves into more cohesive structures, is gaps are opening up in between these galaxies. And that's what the voids are. They're nothing special. They're nothing magic. They're nothing creepy or whatever. It's literally just the place where you've got two groups of galaxies are pulling away from each other, pulling towards to create these larger agglomerations of galaxies. And the gap in between is the void, the place of less density. So you have the places with more density where the galaxies are all mutually pulling themselves together, and the places with less density, which are the supervoids in between. And yeah, as the universe continues to expand, as the universe becomes less dense over time, then We will have concentrations of galaxies in some places, and then vast gulfs in between where there's nothing, and then more concentrations of galaxies. And those supervoids will just get bigger and bigger and bigger over time. Filaments, that's the word. Tejas Dagha. What is the current technology which is being developed that you think will be one of the most useful technology in the future for intergalactic travel? Now, I'm going to say that you said interstellar travel as opposed to intergalactic travel because, I mean, the closest galaxy, Andromeda, like 2.5 million light years away, that just is, there's no way in the near future we're going to be able to cross the gulf between galaxies. Now, theoretically, there's no reason why we couldn't. As long as these galaxies are not moving faster than the speed of light away from us, you can imagine some future civilization being able to reach all of the galaxies in this incredible light cone of space around them. But we can't even reach the nearest star. So let's focus on interstellar travel before we start with intergalactic travel. And in order to go between the stars, you need a propulsion system with a lot more thrust. You need like a chemical rocket. We talked about it in last week's question show, that if you took a chemical rocket, you could feed it the entire universe's worth of propellant, and you still wouldn't accelerate to a fraction of the speed of light. Same thing with an ion engine. It's only when you have a propulsion system where you're kicking out your propulsion at the speed of light or close to the speed of light that you stand a chance of reaching other stars in a reasonable amount of time. And so the one way is to shoot at a spacecraft with a laser beam, a solar sail with a laser beam, because then you can theoretically accelerate your spacecraft to the speed of light. And the other one is a photonic engine. So one where you have a laser beam on board your spacecraft and you fire that laser and it is kicking out photons at the speed of light and you're accelerating your spacecraft. Both have their upsides, both have their downsides. With the photonic system, you need to have electricity to run your laser, and you may require a universe's worth of energy. But I would say right now the most feasible technology that we have is firing a powerful laser at a solar sail to accelerate it to a significant fraction of the speed of light. Edward Casimir. Can we put a giant solenoid on Phobos and protect Mars from solar radiation? I'm glad you asked this question. There has been, this is obviously, let me do this again here. All right. Okay. I'm glad you asked this question. They're very timely. Now, of course, Mars has lots of things going for it. It has dirt. It has a day-night cycle that's similar to the Earth. It has gravity. It's not great. It's 35% of what we have on Earth, but maybe we can make that work. But the one issue that we're never going to be able to deal with is the fact that Mars has no magnetosphere, no global magnetosphere, which means that the radiation is going to be pelting you from space. It's going to be increasing the risk of people getting cancer. Even if we terraformed Mars, made it a beautiful green planet with atmosphere, it would still have no significant radiation protection. And so it would be a very dangerous place to spend a lot of time out there. And so the idea is, how can we give Mars an artificial magnetosphere? And there's been a few ideas that have been proposed. You do it at a local level by essentially building a solenoid into Mars and then building your colony inside this solenoid is one idea that I've seen. You can block the solar wind coming from the sun. You can put a very large, magnetic shield out at the Mars-Sun L1 Lagrange point to block the solar wind, which will prevent some of the radiated particles getting to the surface of Mars. But the cosmic rays, which are the deadly one, you can't stop that because they're coming from all directions. But there was an idea that was proposed just a couple of weeks ago from a bunch of people, including Jim Green, who is the chief scientist at NASA. And this is you're kind of there to use Phobos as a base to help build a magnetosphere that will protect the Mars. But their idea is to release gas, to release particles, an ionized ring around Mars, and then run electricity through it to try and ionize it and form a protection. And according to their math, this should be a way to provide at least a partial magnetosphere for people living on the surface of Mars. We covered this on Universe Today, and so if you want, you can definitely check out that article. It's like a bonkers plan to give Mars a magnetosphere. It's a crazy idea, but some pretty significant people behind it, so I like it. Aliko Tam, are you going to talk about the James Webb incident that happened? James Webb mentions an incident. Sure. Yeah, James Webb, about a couple of days ago anyway, James Webb had an incident. They were connecting James Webb to the launch mount that's going to be on the upper stage of the Ariane 5 rocket that's going to be flying, and like a band slipped off and vibrated the whole telescope when they were doing this operation. And so the mission controllers were a little nervous that this could have caused some kind of damage to James Webb. And so they did an analysis. They took 4 days to do an analysis. So instead of launching on December 18th, now James Webb is going to launch on December 22nd. But they feel like everything is fine. There's not going to be a great big issue. We should be all right. Jimmy Carlson, how much cheaper would a second James Webb cost to make compared to the first? I don't know. You would definitely have some savings because there was a lot of technical risk that was taken on as people were trying to figure out what's the best way to make the actuators work, what's the best way to make the various components work, the science instruments, the sun shield. Like there was stuff going into James Webb that I'm sure if the engineers knew how complicated these problems were going to be, they wouldn't have added this to the project. But now they've essentially figured out how to make these things, how to design and develop for these various science instruments, how to make the actuators unfold the sun shield and the main mirror and so on. And so they could follow in the footsteps, all the technical documents that they did before. But it would still be very expensive. It would be billions of dollars to rebuild the telescope. Maybe instead of $10 billion, maybe it would be $5 billion, maybe $3 billion. I still don't think if they had to, they would be willing to build another James Webb. That ship has sailed. So if James Webb fails, they will just move on to the next priority. I mean, there are already other great big space telescopes in the works, many of which have learned lessons from James Webb. And so even though the telescope would be gone, the lessons learned would still be there and will be incorporated into future observatories as we move forward. But it won't fail. It's going to be fine. Jolly Blonde Giant. Hey Fraser, if we built a really long magnetic launcher, like from the Pacific Ocean up the slope of the Andes, could we get the speed benefits of spin launch without the G-forces? Right, so we talked about spin launch in a previous episode and how the rocket experiences like 10,000 Gs before being hurled off into space. And obviously that would liquefy anything living. Amazingly, there are spacecraft and components that can handle those kinds of forces, but we would just turn into goo. So you need a slower acceleration. And the only way to get a slower acceleration is a longer launch ramp. And something that you're describing where you start off at ocean level and then climb higher and higher up this ramp What I had heard is that you would need a ramp that's like 10 kilometers high, higher, maybe 30 kilometers high. I'm just kidding. What I'd heard is that you would need a launch ramp that was something like 30 kilometers high. And then you would have this big, long part where you're flat and you're accelerating up, and then you're going up this curve, and you could definitely go up a mountain like maybe Mount Kilimanjaro or something like that, where you've got this long, slow curve, and the forces, you're going to feel 2G, 3G as you go up this curve, but you can still handle it. And then you'll be thrown off the top, and then maybe a laser will shoot at the back of your spacecraft and accelerate you to orbit. That would be a mega structured project. And I think before the advent of two-stage reusable rockets like Starship, those kinds of ideas were the only ways that you could get launch costs down by orders of magnitude from existing chemical rockets. But when you look at something that you don't have to destroy any part of your rocket, both parts can fly to space, return to Earth, be reused, refueled, and sent again, then you don't need to get so mega project-y. You don't need space elevators. You don't need 30-kilometer tall launch loops. You don't need just all of these really extreme ideas, because you've got a really inexpensive way to get things to space. And I talk about this quite a bit, that I think we're in a temporary time when we need to launch a lot of mass into space. But there will come a time when we have enough space-based manufacturing going on that the need to launch a lot of cargo to space will go away. And so we're just in this weird, uncomfortable time where we really want to figure out ways to launch more mass to space, but this is temporary. And eventually we'll have just this incredible space infrastructure, and really it'll just be sending people and fancy electronics to space. Okay. Itchy. Gordon Cooper. What is the economic cost of contaminating Mars? That is such a good question. That's like a deadly question. Because, like, what is the economic cost of contaminating places on Earth with invasive species? It's enormous. Here on Vancouver Island, we have problems with rats, with Scotch broom, with various aquatic plants, Japanese knotweed, and the dealing with all of these things it costs a lot of money, and you lose the ability to grow crops, you lose the biodiversity, because you've got all of these various animals and plants and stuff trying to take over and outcompete the native species. But if you have a place like Mars, where life is struggling to survive at all, then if you bring in our cyanobacteria, as my example is sort of your perfect life form, cyanobacteria can just handle anything and just keep going. Send it to space, a year in the vacuum, doesn't care. Bring it back to a nice warm place, or to the conditions on Mars, and it will get going and growing. And so you can imagine our Earth-based life, which has had many, many, many more cycles of evolution, would outcompete the native creatures on Mars. And so you would dig up you'd find this cool aquifer, and you dig into it, and what do you know? It's filled with cyanobacteria. And you open up a interesting rock that's got some water beside it, and what do you know? There's cyanobacteria, because we've infected it. But what is the cost? I mean, it's not like the cost is the loss of the incredible science exploration and discovery that can be made. That if life formed independently on Mars, and every time we try to find those places where it did, we've already infected with our cyanobacteria, then that scientific knowledge is gone forever. And that would be a tragedy, because it would be one of the most important questions that humanity has asked. Are we alone in the universe? Does life form on other places? And we've got this wave of cyanobacteria colonizing places in front of us because we've sent it there. So, but like, what is the cost? I mean, it's not like it's an economic cost. It's like a cost for science. It's a cost for knowledge. It's a cost for the indigenous life forms on that planet. And as we've demonstrated in the past, we don't place a lot of value on it in the moment, and yet we wish we had. And so I think that, like, do I wish that Scotch broom had never been planted on Vancouver Island? Yeah, I sure wish so. And do I wish that rats had never been released on Vancouver Island? Yeah, I sure wish that. And so I think that we should be overly cautious. We should take more time to study and analyze and see and try to figure out the ways to explore without contaminating the local environment to answer the question once and for all if there is any life on Mars. And if there is no life on Mars, then it's just a rock. It's a fancy rock. It's a pretty rock, but it's a fancy rock. And we don't have to be that careful. But if there is life on Mars and it either evolved completely separately or is connected to us through some distant relative, that's a really important scientific question, and we need to tread very carefully. So the way to manage your risk is to be extra careful in the beginning until you feel quite comfortable that there is no life there. Sahin Yasar. What would be Jeff Bezos' business aim if Elon Musk colonized Mars before Jeff? I don't think either Jeff Bezos or Elon Musk really have a business case for colonizing space. There really is no business case. They make terrible business sense. If you want to go and spend the hundreds of billions, trillions, quadrillions of dollars it's going to take to send human beings to Mars, you're not going to make money from doing it. If you're going to spend that money to build infrastructure in space, O'Neill cylinders to colonize the gulf between the planets, you're looking at hundreds of years of investments before you'll see some sort of self-sustaining, profitable economies. And so I don't think either one of them, either Jeff Bezos or Elon Musk, are really thinking about what is the bottom line for this. They want to figure out how they can help fund it. I mean, if you sell people flights to Mars, then that is the way you pay for building up civilization on Mars. If you charge people to fly to space to go and buy property in your O'Neill cylinder, then that helps fund the development of that thing. But I don't think either one of them are planning to try and make money from this endeavor. They're making money here on Earth, Jeff through Amazon, Musk through SpaceX and Tesla, to fund this dream that they have. And I think that if anyone thinks that they have some supervillain plan to make money, like, you should just look at the economics of space exploration. They do not exist. There is no money to be made beyond Earth orbit for space for probably hundreds of years. Whoa, frog. Do you hear about the frog living robots that are made to self-replicate? No. Do you have a link for that? Frogs? That sounds awesome. John Minton. Hey, Fraser, how do neutron stars' lives come to an end if they turn into black dwarfs or explode? So neutron stars, of course, are the degenerate remnants left over when a star much larger than our sun goes supernova. And the star explodes, collapses down, all this material crams into the small area, and you're left with this neutron star remnant, this rapidly spinning object. In the beginning, it's a pulsar because it's spinning so rapidly, in many cases hundreds of times a minute, and releasing beams of energy. And then it slows down over time, and eventually, I guess, stops. I guess, slows down, cools down to the background temperature of the universe. And then that's how it dies, is it just gets cool and stops being exciting. Now, in theory, more material can fall onto the neutron star. It could collect material from a partner, or maybe just like over vast amounts of time, it will collect photons from the cosmic microwave background. It'll collect dust. It'll collect just random shreds of planetoids and interstellar asteroids and things like that. And maybe it could collect enough mass that it would fall over some limit and become a black hole. But we haven't seen this happen yet, but you can imagine in the far future. King David, would it be better to live on a water world than to live on Mars? I would choose... That's a tricky one. I think I would choose to live on Mars because you've got dirt and you've got various elements that you would need to survive. You could extract carbon dioxide, you could extract like iron and magnesium and all these heavier elements out of the soil. There's a lot of stuff to work with on Mars. But if you're on a water world, you've just got water. But water is like the best stuff. I mean, obviously we can drink it. We can turn it into propellant. We turn it into breathable air. So there's all these uses for water. And then in many cases, like if you're on Mars, it would make more sense in many cases to go and live at the poles of Mars where we know there's water ice, as opposed to try to live, say, near the equator where you're really far away from sources of water. And so if you went to a water world, you would need to bring heavier material. You need to bring all of your carbon, all of your metals, etc. But you'd have so much water. So yeah, I think in the end I would go with Mars, but there's a lot of value to a water world. Whoa. Okay. 5 more minutes. Oh, hydroponics. Yeah. Yeah. Good point, Nancy. All right. People are giving me the self-replicating robot frogs. That is amazing. All right. I got to look at this. As people know, that's my greatest dream is to have a robot make another robot. Oh my God, this is so cool. Okay, I'll watch this. I'll watch this after the show. Focus, Fraser. Focus. All right. Gear the Hero. In tackling space junk, I would think that the toughest challenge is capturing the smallest pieces. Has anyone come up with any ideas on how to collect this kind of space junk? The problem with space junk is that every single piece is moving on its own trajectory at, say, 28,000 kilometers per hour. And so it's not like you've got these little pieces of junk and they're all just hovering out in space and you can just grab one over here and grab one over there and put them together and grab a few more. Each one is a bullet and you need to deal with each piece. Even if it's a piece that's a centimeter across, you have to deal with it individually. And so the best idea, what I think is really going to be the only idea, is, of course, with a laser. The Chinese have proposed this and other people have proposed this as well, is that you build a giant orbital laser and its job is to zap pieces of space junk. And it's not going to destroy them, but as the laser hits the piece of space junk, it essentially vaporizes a tiny chunk of the material, the metal, the plastic, whatever. And that causes a little thrust, a little propulsion. And so you got this piece of space junk and the laser zaps it and it gets a little thrust. And so you can imagine it would be shooting these different pieces of junk, zap, 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 as they're all flying past it, giving them all a little bit of a deceleration so that they will all eventually come into the Earth's atmosphere and burn up. There's really, like, you would have to build like on the cheap, if you wanted to build a mission that would collect a piece of space junk, say if there's an astronaut glove out there that you want to recover, you're going to have to build a spacecraft. Maybe it's going to cost you, say, $10 million. You're going to have to launch it on a Falcon 9 rocket. So you're looking at another, say, $90 million, say $70 million. You're looking at about $100 million to retrieve one piece of junk. And then your spacecraft is done. Like maybe you could have a little more propulsion on board so it could go after another piece of junk that's on a similar kind of trajectory. But that's about it. And so you spend $100 million, you've collected one piece of junk, and now there's another, say, 100,000 pieces of junk to go. So no way of collecting things is going to work. You're going to need a way to deorbit them en masse, and really a laser beam is the only way that I've heard proposed that is pretty feasible. Of course, putting a giant mega laser controlled by a country out in space could cause some concerns for various nations. So, so I'll let you know how that turns out. Okay. All right. So I'm going to do the post stuff, and then we will get into the overtime. All right. More questions in a second, but first I'd like to thank our patrons: Terrace Branscombe, Brian Shoemaker, Dusty Reichman, Ed Williams, Bill Nash, Charles Beller, and the rest of our 799 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in a handy audio podcast format, so you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano. And I'm going to do the other outro. All right. Those were the questions this week. Thank you, everyone who asked them. I have so much fun answering these questions. Of course, I record this show live every Monday at 5 p.m. Pacific time on my YouTube channel. There's probably an announcement for the next one already up on my channel. So if you want to come and check it out and ask your questions live, we'd love to have you. All right. We'll see you next week. Okay. All right. Stop the recordings. Okay. So, Frogs, did you pick your username before you learned about the self-replicating robot probes? Do you just narrow in on frog-based stories? I gotta know. I gotta know how this works. Okay. Right. Overtime. Boom. Let's hit the questions fast. There's so many. Cedric Hunter, can we speed up the rotation of Venus? I mean, sure. Yeah, in theory. We would just have to smash it with an asteroid in the perfect direction. We would also make it... But can you make Venus more awful? I don't think so. King David, why aren't there any underwater cities here on Earth? Good question. Because ocean is actually harder to explore, harder to live under than space. With the ocean, you go down a few hundred meters and you've just got enormous forces pressing down on your city. So it's actually like space has been better explored. The solar system is better explored. The surface of the moon is better known than the bottom of the ocean. We have mapped Mars to within 30 centimeter resolution across the entire planet Mars. And yet we don't have any kind of resolution for mapping the seafloor of the Earth. There could be all kinds of things down there. It's just that the ocean is so hard to explore, even though it's right there. I mean, I can go swim in the ocean. Well, maybe in the summertime. BEM Woolgast, what are your thoughts on the paper published today in Nature Astronomy suggesting that much of the Earth's water may have come from hydrogen ions and the solar wind interacting with dust on asteroids? I don't have an opinion. I perused it briefly and threw it into the story queue for one of my writers to write on should they choose. Let's see if anyone actually grabbed it. I don't even know. Nope, so far nobody's claimed it, so there you go. Who knows if we'll be reporting on it. But yeah, the idea is pretty cool that essentially you've got material, hydrogen coming from the sun through the solar wind. It's interacting with volatile elements in dust and then turning into water and landing on the Earth. And it would be pretty crazy, pretty exciting if that's true. Because one of the big mysteries in planetary science is, where did all the Earth's water come from? Did it come from comets? Did it come from asteroids? Was it just picked up, slurped up in place by the Earth as it formed? We just don't know. But if hydrogen streaming from the sun interacted with oxygen and turned into water, that makes sense because the sun is doing this all the time. Then maybe we would see more water forming. I don't know. It's a clever idea. I like it. Stephen Long, would you rather live on Mars or the moon? Neither. I want to live on Earth. But I guess I don't have a choice, right? So Mars or the moon. If I can't live on Earth, I have to live on Mars or the moon. Mars. I think Mars. I mean, they all suck. So both suck. So what have you got going for you on the moon? The moon, you got the lower gravity, which would be kind of fun, but then you get bored of that. You've got a worse landscape. You're going to have to live underground on both. Mars, you've got sunshine, dirt, regolith. Yeah, they both suck. Yeah, Ruling Moss says I'd pick the moon since it's closer to Earth. Yeah, but I mean, if you can't go to the Earth, you just have to look at this planet that you can't live on anymore. Yeah, I would probably pick Mars. But it doesn't matter, right? Like, do you want to live in an underground tunnel that's kind of gray or kind of red? Which underground tunnel do you want to live in? Colonel Zach, what's the last space fact you learned that truly blew your mind? I don't know. Man, I wish I this stuff cycles through my head so quickly. I like the idea that 94% of the observable universe is inaccessible to us, even if we could travel the speed of light. That we could only explore ever 6% of the universe. The rest is going to fall over the cosmic horizon and disappear, and we could never reach it unless we could figure out a way to go faster than the speed of light. I mean, it's neat, but it's also sad. But I like it. John Pritzlaff, Fraser, colonizing wormholes viable in the far future? Well, we would have to know if wormholes actually exist. So if wormholes actually exist, then we have to find out if wormholes are traversable. And if wormholes are traversable, we have to figure out where they go. And are you really colonizing a wormhole? You're just using it as a door to some other location. So. Oh, the bots showed up. Wow. This is a hell of a thing. Isn't this like a big problem on Twitch? I didn't realize that the bots were so hardcore on YouTube as well. Huh. Wow. Go, Nancy, go. XML 7SX. What are your thoughts on the nuclear test ban in space? The only place I think we need nukes. And will politics complicate an eventual asteroid redirect mission? Thank you for everything. Yeah, I mean, the nuclear test ban was done, say, as part of the Outer Space Treaty a few decades ago. And the whole issue with that was that you had the Americans and the Russians really not wanting to have nuclear weapons out into space. Because right now, if you say launch a missile from some location, then you've got 45 minutes, an hour to figure out if you're going to defend yourself and fire your nuclear weapons back at them. And so, but if you have orbital nuclear weapons, then you could have a weapon that is flying directly over your enemy, and then you just fire the weapon down, and within a minute, you're detonating it over their cities. And so there was no way to have any kind of deterrence. And so that was the reason why they negotiated the ban of nuclear weapons in space. And so, yeah, I think it's great. Yeah, no nuclear weapons in space, please. Now, I think that there should be some kind of rules for, nuclear reactors in space, that there should be nuclear propulsion systems in space, but definitely there should not be nuclear weapons in space. I mean, there shouldn't be weapons. There shouldn't be nuclear weapons at all. So let's also not have them in space. Okay, close that. It looks like my racist uncle finally learned how to use the internet. Yeah, definitely feel free if you're watching this to report any of this stuff. Three-thirds nerd. Will there be live star parties again? Eventually. So we were close, where we had the remote observatory that I was using thanks to Oceanside Photo and Telescope. But the problem was, because the telescope was far away and required too much maintenance, we weren't able to keep it rolling. And so there was still too many cancellations, and I just didn't like it. So my new plan is I'm building an observatory here, and I'm going to host it. And so when I have clear skies, which is summertime, very, very rarely in the wintertime do I get clear skies at night. But once I do, I will do star parties. And then my plan is to then stream my view, but then also bring in other people, other friends, etc. Anyone wants to join and hang out and do it at the same time. Or like bring in special guests who maybe have no experience with actually doing astrophotography, and then we can just chat and hang out and do astrophotography together. So I would say at this point, I'll probably be building the actual observatory in the next 6 months, and then I'll get a relatively fancy telescope. That's my plan right now. Good job, Nancy. That was a hell of a thing. All hail Nancy. Oh, we got Noel there as well. Okay. Why don't you choose to live in a place with as many clear sky nights per year as possible? Well, because there's other benefits to living on the west coast of Canada. So living in a temperate rainforest, it's paradise. It just is rainy a lot. That's how you can't get a rainforest without rain. Love your guests and letting you lead the discussion. Yeah, we'll see. But I like the problem, and maybe there's other ways that I can solve it, but we tried to go the remote observatory route, and even that wasn't dependable. And so I think having a telescope that I am really familiar with. It's right next door to me that I can go and kick and make sure it's ready to go. It's using my internet. The speed will be fast, and then do it whenever I have clear nights is, I think, the plan. But we'll see. I mean, it is a tricky, challenging thing to do. I mean, it has, like, without money. Like, obviously, you know, if I had lots of money, I could just build a suite of remote telescopes around the world and have people manage them and spend $100,000 a year to make no income. So, but the way that I do it without spending a lot of money is I just have a telescope nearby that I can use. Okay. All right. I think we're going to wrap things up. So thank you everybody for hanging out today. This was super fun. Thanks to all the mods, especially Nancy and Noel and the others today. You were definitely in mod hell. So again, thank you. And I appreciate all that you do. We will be back. Got a bunch of cool interviews coming up. So stay tuned. I'll post them shortly once I've got them locked in. But anyway, thank you everyone. Super fun. And we've got another question show that's edited, and I'll release it probably tomorrow. So stay tuned for that. All right. Thanks everyone. We'll see you later.